Hey guys, this is JB from Planning Seeds Tutoring. In this video, we're going to be talking about Bohr diagrams. Bohr diagrams are supposed to be a depiction of how atoms were originally believed to have looked. Anyway, don't forget to use my referral code JBMon20 to receive 10% off on your next tutoring package. So again, a Bohr diagram, or the Bohr model, it was created by Danish scientist Niels Bohr, brilliant scientist by the way, in the early 20th century. And this was like a very early depiction of how atoms were thought to have looked. So, well, it kind of looked kind of like this. Well, actually, for sodium, it's actually going to look exactly like this. This is the element for sodium. By the way, we're going to be using the periodic table of elements. That's why we have this one open. This is from ptable.com. So for sodium, here's our Bohr model. We have protons, 12 neutrons, one ring with 2 electrons, another ring with 8 electrons, and one last ring with 1 electron. So this right here, this depiction right here is supposed to be very, very similar to the solar system with their planets and the sun in the very center. And the Bohr diagram, well, what Niels Bohr's kind of like logic was, well, it would have been essentially perfect if our solar system or universe, all the macroscopic objects are moving inside of this solar system in kind of like a orbital kind of pattern. Well, why not have microscopic or extremely microscopic atoms and stuff also follow the same nature? That would have been like the most perfect kind of situation. However, in reality, that's not true. And he soon kind of figured this out. In reality, it looks more so like a cloud of electrons, a little bit fuzzy and stuff, not entirely like a sphere. It's supposed to look more so like a spherical, dense sphere with just a lot of like different places where electrons could be. It's all based off of probability and stuff. Very, very difficult to comprehend with like a very, very, very tiny center. This image right here is already like over exaggerating how big this nucleus itself would be, but yeah, this right here would kind of show in general what the actual, at least from what our knowledge today is, would kind of show like a probabilistic kind of sphere, which is how like our current understanding of science kind of shows atoms to look like. Well, these diagrams though, at least these diagrams are kind of very hard to work with, but the Bohr diagrams, they look very easy to work with. Simply because you can see the number of electrons, it's very easy to kind of work around with. Whereas here, all these electrons are supposed to like jumbled around, moving around, etc. Don't forget, by the way, electrons are like 1,000 times smaller than like the smallest protons and stuff. I mean, than protons and neutrons, but they are essentially, the electron density would be pretty low, essentially. Anyway, going into the Bohr model, this right here is, remember, a Bohr model for sodium. Notice we have a few rings around the central circle, and inside of the central circle we have the number of protons and the number of neutrons written. And inside of these other rings, we have electrons that are supposed to be orbiting or circling around the nucleus. In fact, this diagram did get that correct. The electrons would actually be orbiting around, or not necessarily, or they would be kind of circling around, not necessarily in like a perfect circular fashion, but they would be around the nucleus, and the nucleus itself would be carrying a net positive charge because it would have protons and neutrons. Quick note to recognize. P plus, that stands for protons. E minus, that stands for electrons. And N0, that stands for neutrons. Just indicates the subatomic particle with their respective charges. Protons with that positive charge, electrons with a negative charge, neutrons with a zero charge. Anyway, let's try making a Bohr diagram for carbon. So the first thing that you want to recognize is, or at least count, would be the protons, the number of protons for carbon. So let's write down carbon. Number of protons would be, well, for carbon, actually, in fact, for any element, just looking at the atomic number would get you the number of protons the element has. So for carbon, as you can see, carbon is the sixth element, which means its atomic number is number 6, and therefore it has 6 protons. Number of neutrons, let's hold off on that. Number of electrons, if you're working with like a non-charged element, it's going to always be the same number of protons because, well, each proton carries a +1 elementary charge. Every electron carries a -1 elementary charge. Just to cancel it out. So if you have 0 charge, that means you have to have equal number of electrons and protons. Another thing that you want to recognize is the number of rings that your carbon molecules or carbon atom is going to have. Well, the number of rings is just going to be the row number that you have. So hydrogen and helium, they're in the first row. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they're all in the second row, and so on. This means that carbon is actually going to have 2 rings. Finally, you want to recognize the number of valence electrons. Number of valence electrons can be counted based on the group number. Groups 1 and 2 are going to have 1 valence electron and 2 valence electrons respectively. So hydrogen would have 1, beryllium would have 2. Groups 13, 14, 15, 16, 17, 18 would have 3, 4, 5, 6, 7, and 8 valence electrons respectively, except for helium. Helium's actually only going to have 2, but there are a few exceptions for every rule. So in this case, carbon is number 14, which means it has 4 valence electrons. All right, so let's try drawing this out. Well, quick thing to recognize, center tells us number of protons and neutrons. Well, actually, I kind of should tell you how to count the number of neutrons first. To count the number of neutrons, you want to first identify the mass number. So the mass number is going to be the number of protons plus the number of neutrons. Generally, you would either be given it in terms of someone would either say the element that you're working with is, or the atom that you're working with is carbon 12, carbon 14, carbon 13, etc. These are all different what we call isotopes, which I'll get to in a moment. This number right here tells us the mass number. So all you would need to do here is subtract out the number of protons which for carbon is 6, the number of protons is always constant. It's always the same as the identity number, or the atomic number. So you just subtract out 6 and you should be able to get the number of neutrons for this scenario. So for carbon 12 you have 6 neutrons and 6 protons. For carbon 14 you have 8 neutrons and 6 protons. In general, whenever you're working with them, they're not giving you, they didn't give you like an actual number to it. Well, you just use the weight. So here, carbon's weight is 12.011. That rounds to about 12, which means it's going to have, well, 6 neutrons. Now we're ready to draw it out. So first circle is going to give us number of protons and number of neutrons. So 6 protons, 6 neutrons. Second circle is going to be our first ring. Third circle is going to be our second ring. We don't have any more rings. Now let's actually start filling up the rings. Our first ring can only have 2 electrons, a maximum of 2 electrons. This is true for any element. Our second ring can only fit up to 8 electrons. This is true for any element. But another ring that can only fit 8 electrons is the last ring. In our scenario, our last and our second ring are both the same, so regardless it would have been 8. And that's because you can only have up to 8 valence electrons, and the last ring shows the number of valence electrons. Here we have, for carbon, we have 4 valence electrons. 1, 2, 3, 4. Now you might be wondering, why did I draw these electrons in terms of like pairs versus singlets? And that's because, well, electrons are actually divided into groups of what we call orbitals. And inside of these orbitals, they're like supposed to be partner electrons. You always have one spin up electron and one spin down electron. And you can only have a maximum of 2 electrons inside of these orbitals, but you can't have just one. You can also have just 0 as well. So in this case, you have, well, in the second energy level, you have 4 orbitals. In the third energy level, you have more orbitals. In the first energy level, you only have 1 orbital. Inside of each of these orbitals, you only have, you always fit in up to 2 electrons. And that's why I kind of drew it kind of like this. Thing to recognize though is we need to follow Hund's rule. Hund's rule is also known as like the school bus principle, which states that electrons fill in every single orbital. Like they go to the most open orbital first. So if there's an open orbital, they go to that one first before trying to get into another one's an already half-filled orbital. All right. A quick thing to note is something about isotopes. You've probably heard. Isotopes are atoms with the same number of protons but different number of neutrons. Same protons but different neutrons. Well, so if you have different number of neutrons, this means that you have different mass numbers. Another thing that you have are ions. Ions are atoms with the same number of protons, but different number of electrons. When you have less electrons than normal, that's when you're called a cation. Cations means less electrons than normal. Normal referring to like the neutral state. So for like it just refers to the same number of protons as the number of electrons. Or the zero state. Anion is going to be more electrons. If you have less electrons in cations, you're going to have a positive charge. If you have more electrons, as in a cation, you're going to have a negative charge. An atom can't ever have a different number of protons, since protons are what give the atoms their identities, and it's always the atomic number. And differing Bohr models exist depending on whether or not you have an ion, isotope, or just a normal atom itself. Let's actually try making one for the sodium cation. For a cation of sodium. So here we actually already have one for sodium, but a cation for sodium would be missing an electron. Well, if we're missing an electron, we generally take away this electron from the outermost shell. It's going to be from here. Generally take away this electron right here. Well, if you're missing that electron, that means there's nothing in this last shell, which means we can just kind of get rid of this last shell. This means that the entire atom right here just got a whole lot smaller in terms of atomic radius and stuff. But this right here would be our Na+. Same number of protons, 11 protons. All right. A quick recap. First thing, whenever you're trying to solve for, when you're trying to make a Bohr diagram, first find the number of protons, neutrons, and electrons for the atom. Next, draw a circle to represent the nucleus. Next, draw the number of rings that match up to the row number of the atom, and then fill in the circles based on their order. All right, thanks for watching, and I hope you all learned something new.